All right, shall we get started?
Yeah, go right ahead. Floor is yours.
All right, everyone. Well, thanks for coming. I hope you're having a great time at QHack. Must be really fun. Today, we're going to talk about quantum chemistry workflows on quantum computers. On today's menu, first, we're going to go over an overview of what Tangelo is, and then we're going to explore a little bit all the online resources that are available. They are mostly on GitHub. We're going to do a little demo just so that you can see it in action and not get bored by just slides and me talking about it. And then eventually we'll just wrap up. So first, for an overview, what is Tangelo? Right now, in the field of quantum chemistry, we can't just take a molecule and just throw it at a quantum computer and get something nice, reliable, and useful from it. We have to be a bit smarter than that. It's a bit more complicated. We have to kind of build entire workflow to massage like these chemical problems to make them more amenable with quantum exploration, with simulators or with devices. And that's really with that approach in mind that as a group researching chemistry and wanting to apply quantum computing to it, that we approach our work with Tangelo and our R&D. From the definition of a molecular system to picking an algorithm to eventually taking it to one of the many awesome quantum circuit simulator or quantum devices, and eventually post-processing the results and repeating that until you get something meaningful. Tangelo is an open source Python package with very permissive license, so it plays well with the whole Python ecosystem and many exciting projects around. And really the goal was to accelerate the R&D and the learning on quantum computing, the field of quantum chemistry, focus on experiments, and make the most of it to accelerate R&D. And that was really central, is that when we came up with Tangelo, what we really wanted to come up with an engine to accelerate research. There were many tools around, but they were not quite fitting the bill, and we decided to implement our own approach. Two big things for us was to do quantum algorithm R&D, to easily prototype new approaches and compare it with existing ones from the perspective of the accuracy, like how accurate in terms of quantities that are relevant for chemistry approaches are, or in terms of resource requirements, how many gate, how many qubits, how many measurement, how close they are to quantum technologies and their capabilities. And the other one really is that we wanted to do hardware experiments. We wanted to play with these nascent quantum devices that are proliferating in a positive way, and to stay connected to the development of the technology to essentially understand, okay, how far, how close are we to leverage these powerful devices to do something meaningful in chemistry, or to at least better understand how they work. And again, this is an engine to accelerate research, so we wanted to make sure that essential steps in our learning and research were covered. That is, we wanted to build something that really helped us prototyping new approaches, reproducing all of the amazing research that is being published almost every day, benchmark different approaches and compare them, procure our own innovation, or let people innovate in general, but of course integrate this innovation back into the software so that we can keep this virtuous cycle going. So that's really the philosophy, I think, behind Tangelo. Now, what does it look like? Well, basically, the idea of Tangelo is that we wanted to take chemistry to any quantum platform. For us, that was a requirement. If we wanted to do good chemistry, if we wanted to leverage all of these cool technologies that was emerging, we had to kind of develop a library of toolboxes and algorithms that allow us to take interesting chemistry problems and then build something that could run on, these many devices and simulators to study chemical system. On the top of this slide, you have a layer that is what I call the application layer. That is mostly about chemistry or about toolboxes that do not need to know what hardware or what simulator is being used to simulate or execute a circuit. In blue, you have basic toolboxes that contain functioning classes that are fundamental building blocks. For example, we have some to help us map a molecule to qubits. We have some toolboxes to post-process results that come from outside a quantum device to kind of like increase the accuracy of a result, deal with noise, or reconstruct quantities of interest. And then we have toolbox for molecular computations. We have toolbox to help you design a measurement strategy. It's very varied, and there's so much more. Then we have another kind of bigger building block. We have entire algorithms in there. It's not just variational approaches, even though like people are very excited about VQ, there's so much more. We don't discriminate between NISQ or fault tolerance. There's classical solvers in there to help you get reference results. And in the fault tolerant, you have algorithms around phase estimation, imaginary time evolution, everything that has to do with Hamiltonian or time evolution, and much more. And on top of that, you have another building block that we call problem decomposition. In our work, we always wanted to make sure that we could tackle systems that go beyond toy models, beyond the H2 or the lithium hydride that everyone starts running experiment on. We're going to talk a bit more about these techniques, but essentially they can help you scale to study what quantum computers could do as part of more, let's say, industrially relevant problems. On the bottom layer, we have everything that has to do with what I call compute backends. So we can connect all of these building blocks or these algorithms to cool simulators developed by the community, some developed by us. You can see a few names that you know already, as well as quantum devices developed by, I don't know, like a number of big players and smaller players. And last but not least, you can also define your own custom backend. If you define how, for example, a quantum circuit is simulated with your own code, regardless of what that code is doing, or how to compute an expectation value, you can kind of plug that into algorithms to decide how they run. That was a lot of information right now. So we're going to see in the next slides what it looks like. This overview doesn't look too much at code, but we'll jump in a bit later into it. What was really important is that we have a tremendous ecosystem around quantum and its application. And we believe that if you want to do good research in that field, you should be able to harness all this innovation that's scattered across this domain. You should be able to leverage all of them together. And in the design of Tangelo, we wanted to make sure that, for example, key quantum quantities like operators or circuit were easy to translate, to build bridges between all of these different frameworks, and to make that as simple as possible for you. So on the bottom right, for example, you can see a glimpse of what these translation functions look like that just take a target and a source format, and you're pretty much done. And the goal of that is that we don't want people to spend too much time on APIs and connecting the software they need if they're not interested in that. They can focus on the high level. The big question: how do you want to approach this chemical simulation and the modeling? For example, what kind of algorithm and strategies do you want to use? What kind of quantum algorithm do you want to apply, study, compare? And finally, at the high level, well, how do you want to simulate or execute that circuit? Do you want to use a particular simulator or device? Do you want to use shots? Do you want to use a noise model? And the goal of that is really, you want to spend less time on the nitty-gritty sometimes, and you want to like be at the high level and be more in command of really what you're trying to achieve on the science. And you want to leverage all these tools together. That being said, convenience is great, but fine control is important for experts and researchers. So at the end of the day, you can always go down essentially with toolboxes and kind of explicit everything yourself. You're not tied with this high-level abstraction that we provide. Earlier, I mentioned problem decomposition. And for us, that's something we've been interested since our early days at Good Chemistry, or even 1QBit before that as the chemistry division. We believe that in order to do interesting things in chemistry, it's important to leverage what the field of chemistry has figured out in order to scale to larger molecules and bigger problems. We have an array of what we call problem decomposition or fragmentation techniques that can be useful for different fields, such as battery chemistry, discovering new functional material, or biochemistry. You can see a few names of what these techniques are, and they're available in Tangelo. Chemistry is also about leveraging all the insight that we have about the problems. Chemists and physicists can predict in advance that in your system, in your molecule, in your electrons, for example, some of these electrons are not going to contribute meaningfully to the problem. So instead of just trying to force the entire molecule essentially to a quantum computer, well, you can be smart and know in advance that there are parts you can cut off to reduce the complexity. And what does that mean? Well, it means you can look at bigger problems. It means you can do more with a restricted quantum device or the simulators that we have today. And finally, on terms of mean field calculation for the modeling, you have a bunch of different things. I don't know how familiar everyone is with chemistry here, so I don't think I need to go into detail. Something interesting to mention is that we've also implemented in a different platform, because we've been always interested in chemistry, but we're not only doing quantum computing. This platform is called Chemist Cloud, and we implemented this method called incremental FCI, IFCI, that we scaled to essentially run to up to 1 million cores in the cloud to tackle very hard problems that have to do with the biodegradation of what we call forever chemicals. So we essentially went to tackle a very hard problem with that. And there are blog posts available on AWS blogs. One is HPC related, which is this million core run I just talked about. But there's also another one to see how Tangelo and quantum computers can be paired with this decomposition IFCI to start to see what a quantum computer can do as part of a bigger, more scalable approach. We talk about algorithm, and I don't want to talk about VQE. Like, everyone is talking about VQE already, but I think it's a great example. We don't just simply implement algorithms. Our philosophy is that everything should be extendable, everything should be flexible, because they are merely a building block, and we always need to go further. If you're interested in playing with VQE, well, you should know that there's more, for example, that just Jordan Wigner and the BraVQ type of qubit mappings for mapping molecules. We have at least 5 of them in Tangelo, for example. People can provide their own Hamiltonian. If you're interested in playing with different ansatz for VQE, well, we got more than 10 already available, but you can also provide your own variational circuit and explore that. Same with the optimizer. You may want to control that. You can actually plug in anything. Any function, regardless of what library it uses, can be here to dictate how the optimizer works. And finally, you should be able to plug in easily a different backend on your VQE. Do you want it to be noisy? Do you want it to be a particular type of simulator? Or do you want to define your own? Well, you should be able to do that. So here is just an example of a very strong philosophy in Tangelo that for every algorithm, for all these building blocks, we try to provide convenience. That is, people can just do things rather easily, but also fine control. If you want to tweak that thing and take it in a different direction, if you want to implement something new, something different, you have access to these building blocks and to easily modify things to do your own thing. And this is not the end. Again, VQE is just a building block. You don't want just an algorithm. All of the algorithms for us tend to track computational requirement. You have very easy ways to access how many gates, how many qubits, how many parameters, how many terms, for example, in VQE or other algorithm, the approach required to see if it's relevant or not. You always want to potentially extend them. For example, VQE has many flavors. You may have heard about adapt VQE, about the state average orbital optimized VQE, about the quantum qubit cluster. Like, essentially, all these algorithms are available in Tangelo, and they're built upon VQE. We keep building up. You can keep building up. And finally, we're building entire workflows, right? It's not just you can push any molecule into VQE and it's going to give you a result. You're going to be stuck with small molecules. It has its own challenges. So you should be able to combine them with other things. And for example, problem decomposition to look at bigger systems. And last but not least, hey, we want to do chemistry. So we want to make sure that we are able to look at interesting systems with the resources we have. So VQE, for example, here in Tangelo is compatible with open shell systems, compatible with active space selection to, again, trim the electrons and parts of the problem you know are not interested. You can study more than ground states. You can also look at excited states with VQE as well. So essentially, the bottom line is that it's not about just finding an algorithm and writing it. It's about building a framework that can take people further than that. And that's a strong philosophy in Tangelo. We talked about VQE, but essentially, you'll see it a bit later. We have a lot of building blocks around like fault tolerant algorithms because we think that they are meaningful. Multi-control gates, block encoding, time evolution, measurement control gates, frameworks for algorithm like QP. If you're familiar with fault tolerant, you may have a lot of fun with Tangelo to try to build these new approaches. There's one thing that a lot of people don't talk about, and it's hardware experiments. We're very transparent. Actually, we usually disclose the entire hardware experiment process that we have in open source code and publications. And submitting circuits to a quantum computer is actually the easiest part of a quantum experiment. Like, there are big questions that come before and after that can take a lot of work, a lot of reflection, a lot of coding as well. The big questions you're trying to answer before running an experiment is whether or not the experiment is going to be within a budget. Because yes, you are working under constraints. Quantum computers are not a commodity, it's a scarce resource, and you're working either with a budget in terms of money or time on the machines, right? There's only so many circuits, there's only so many measurements you can take in order to collect data and hopefully do something interesting within and learn something. And the other question is, what is the likelihood of success? If I'm throwing all of these things at a device and I get noisy results, because currently devices are noisy, can I hope to actually extract meaningful information that make me learn something or that help me doing something for, I don't know, a publication and pushing the boundary a little bit? So before you run an experiment, you're trying to answer this question, and has to do, for example, with resource estimation. How many gates, how many qubits, how many measurements? Can you simulate the behavior of a noisy device to have an idea, okay, what's going to potentially come out of that thing? Is it just going to be noise and then there's nothing I can do? Can you simplify your circuits to maybe raise your chance? Can you define a better measurement strategy to try to make the most of your time in this device? And you know, well, after you send all of these instructions, these operations to a device, you get a bunch of histogram. Not the sexy one that you see on the right that has the bars and everything. Like, that one looks nice, but in reality, you're just juggling with a lot of numbers in all directions. And there's a lot of stuff you're going to have to do with that. You're going to try to aggregate them to recompute quantities of interest for your application. And maybe you're going to have to deal with noisy results. Maybe you're going to have to post-select some of them to renormalize, to map back these quantities to something of interest. Maybe you're going to have to remove ancillary qubits from all these histograms. Maybe you're going to have to resample this histogram. Maybe you're going to have to estimate the error bars. What is the expectation value? What is the variance associated with your experiment? And in there, you're going to throw maybe some chemistry inspired post-processing, because you're doing chemistry, so maybe you have some insights about what you should be doing. And it's interesting, I won't spoil too much about it, but last year, someone in our team ran an experiment that literally required thousands of quantum circuits. So we have applied this tool to go through volumes of data to try to extract the most information possible from what came out of a quantum computer to learn something and to share it with the community. So hopefully in a few months, you see that coming out, keeps your eye peeled. But really, hardware experiments are tough. And, well, we just need good tools to do that. All right, that's a lot of talking. I've been talking for like almost 20 minutes already, but you haven't seen much, essentially, of what we have to offer you, what you're going to interact with. Let's get into the online resources in the GitHub, because most of the stuff is on GitHub. There's one big thing I just want you to remember is that Tangelo comes with a community and a lot of educational resources, a lot of tutorial, a lot of documentation, some blog posts, all with the idea that we're not just showing you how to code stuff in Tangelo, but these things are meant to help you understand with some hands-on as well, things about chemical modeling, how quantum algorithms work, and how hardware and hardware experiment works as well. So even if you're not using Tangelo, I think these are wonderful educational resources for you to dig a little bit into the topic, maybe look at the references and the articles and whatnot. Let's have a look, shall we? You should be able to right now see a web page. If you don't, someone please scream at me. This is the repo for Tangelo. It's still under Good Chemistry, but Good Chemistry has been acquired by Sandbox, so it will be moved soon, and this will have no repercussion on Tangelo users. This repository contains all the code, but it contains so much more than that. You have the usual installation instructions and everything. It's a Python package again, so you are free to install it directly with pip or from source from the GitHub as well. What's interesting with Tangelo is that it comes with a lot of resources. We have a vibrant ecosystem and all these open source projects, right the state of the art, so many features. We're trying to keep people up to date with simple visual. If you want to keep track of what's in Tangelo, you can just click, for example, here, and you see, stuff that's related to the quantum chemistry modeling, stuff that's related to the actual quantum algorithm, and stuff that's related to quantum devices, for example, which is a nice way to get, like, at a glance, the capability of what we have before you dig into it. And I think what's very interesting for you is that, well, we have an entire repository that's called Tangelo Example dedicated to examples and tutorials. And we have a large amount of tutorials, and we find that people have various interests. So what we started to do is we tagged all this tutorial. You can look at the tags here to see what things are talking about. You're interested in introductions, for example, you can just look at one of these introduction notebooks. You love variational algorithms, that here you go. There's 4 of them here tagged with VQA. You're interested in problem decomposition, you've got all the red ones. And if you want to read about actual hardware experiments that were run on various kinds of device, IBM, IonQ, or through Amazon Bracket, for example, well, you can have a look at that too. Pretty much every single topic we have discussed so far has at least one tutorial there, essentially, for you to explore. There's something very interesting too, I think, is that if you have a Gmail account, basically you can click this button, Open with Colab, and you're able to get started right away without doing any sort of installation on your machine, and to explore some of the resources we have, some of these tutorials, but also some hands-on, essentially, that we've developed, which consists in a series of small exercises that people can go through and complete some code to learn about it. Here's, for example, a cool hands-on that coworker James Brown made about fault-tolerant building blocks. You're interested in fault-tolerant algorithms? Well, here we go. We just guide you with some essentially different steps and building blocks. We describe what control operations are, and we ask you to insert code to maybe solve small problems and everything. And we just keep going. You can learn about quantum phase estimation and how we can build it from scratch with all the building blocks in Tangelo, or simply directly reuse the framework and have an idea of how to interact with the quantum algorithm, passing options, building, simulating, and reconstructing key results. And it goes on with blocks encodings, amplitude amplification, like, essentially, you are very much guided. Whether or not you want to learn about simple topics or more complex ones, there are resources in Tangelo to help you achieve that. I'm going to close that. But the bottom line is we have a lot of educational resources from you, and whether you're a newcomer or a seasoned expert, we believe that Tangelo can equip you to explore some of these topics. Alrighty. How about we do a little demo now? I've been talking about this for a while. It's a bit more concrete, but still not concrete enough. Here I'm taking an old story that we talked about in 2019. Back then, our team was part of 1QBit. And I want to show you how a few different functionalities can come together to give you an idea of the challenges that we face and how we try to tackle them. I clear on this notebook just to get rid of all the installs and everything here.
Hey, Valentin, do you mind just zooming in just a little bit? I think it's,
Yes, I can. How's that?
Maybe a couple more.
A couple more.
There we go. That's perfect. There you go. Perfect.
That's very zoomed in. I hope most of the stuff is
perfect.
All right, fellows. Well, this is not very interesting here, but basically, Tangelo can be easily installed from pip, and then all the dependencies, whether they are one of the many chemistry packages we leverage, PySCF, Cypher, RDKit, OpenMM. The open source community in chemistry, quantum chemistry, is also pretty rich. Or whether they are other tools you may have heard about developed by other people in the field of quantum computing. Let's have a look at this small use case, which is a ring of 10 hydrogen atoms. It's a very simple system. And in Tangelo, it's fairly easy to just kind of read that in. If you just provide the coordinates of your atoms, you can build a molecule object. And if you print that object, you will see that many things have been computed about what we call the mean thing energy, how many electrons, how many atoms, how many orbitals in general, what kind of Milfin was computed, right? So you can access information in objects very transparently in general with Tangelo. You work with quantum, but you always want to know where your approach sits in terms of accuracy compared with ground truth, or at least with the closest thing you have, which usually is classical simulation. So Tangelo easily provides, for example, as algorithms, what we call solvers. Here's two classical ones that use classical computing to get some answer about the ground state energy of this molecule, which is a quantity we're going to be interested in here. If you try a good old approach with VQE, the vanilla one that everyone probably learns when they get started with what we call a UCC ansatz and maybe a qubit mapping that Jordan Wigner, here's how you do it with Tangelo. You import this as an algorithm. You can use some of the built-in ansatz to say, I want UCCSD. You can just specify, I want Jordan Wigner. You push your molecule in, and you build an object. We separate the build from simulation because simulation can be really tough, really expensive, take a very long time. So before simulating, you may be interested in knowing what are the resources that my algorithm take, how complex it is. And at this very small problem, if you have a look for this VQE, you can see the number at the bottom. Wow. We see that we're in for a circuit that requires 20 qubits, that's the width. Okay, that sounds manageable for like simulators and whatnot. But you can see that the length of this circuit is like 30,000 gates. Right now, most gate model devices can maybe hold 10 or 20 of them before the results are drawn in noise. So clearly this approach is not going to give you anything on quantum hardware, even with infinite time. But even with this simulator, like, we're trying to optimize parameters in a high dimensional space of size 350. This is a very big challenge for like an optimizer. If you have a fast and efficient like quantum circuit simulator, well, I'm not quite sure you're getting something out of this. And it's probably going to take a very long time to finish with your optimization, right? So the bottom line is that if you just try with vanilla straight out of the box approach right now, you're most likely not able to study this system. And that's how, for example, tools such as problem decomposition can get in there. So earlier we mentioned DMET as one of these tools. What DMET can do is to really chop these molecules into what we call fragments, and then kind of compute quantities of interest on this fragment, and then remerge everything to get the answer to your original problem. So instead of solving a big hard problem that's out of reach, You're trying to solve a more or less equivalent collection of sub-problems that are a bit more tractable. The approach works just like for any other algorithm. You pass usually a dictionary of various options. I pass my molecule here, and you've seen my ring of hydrogen atom is very symmetrical. I'm going to basically ask the MET, can you aggressively chop this molecule into 10 fragments of 1 atom each? And because all these fragments in this particular case are the same, I'm just saying, okay, solve one of them with VQE, and you can solve all of them, the rest of them, sorry, with a classical, essentially, solver. And as well, I'm just building my object, and I'm just having a look at the resources, right? And we see something that is much more tractable. Suddenly, we find circuits that only have apparently 14 gates, right? And they only require 2 qubits for this particular fragments, and there's only 2 variational parameters to optimize. So suddenly, a problem that was just intractable becomes like much more tractable. If you want to look at the fragments, this is what you look like. This picture was made with another beautiful software from a chemistry ecosystem, just to represent what we're looking at here. With a simple call to simulate, I can basically do all the simulation. Here, everything would be done on a quantum simulator, and within a minute or so, we get an answer. When you can see what this approach yields. So we get a number, and I can compute the difference easily between this number and my reference value from earlier. So you get here something that's not quite at what we call chemical accuracy, but that's a result of the approximation made by the MET and made by applying VQE to calculate the energy of a fragment that eventually gives you the total energy of the system. So you get an idea of essentially how your entire workflow gets more or less close to the ideal value, the ground truth, or at least the best thing you have from it. Segue into that, great, you have run something on a simulator, but what if you want to explore that on a device or manipulate that further? Well, for example, here you can easily retrieve the information. You can retrieve that final optimized circuit with that simulator. And then if you want to go onto another framework, you're like, okay, I'm done with Tangelo. I want to move with like another framework. I want to take that to a quantum device, or I want to do my thing, right? You're welcome to. With just a simple call to here a translation function, you can get the equivalent Qiskit object. And then you can manipulate this Qiskit object just as easily as you manipulate Qiskit. You are effectively manipulating Qiskit. I think Qiskit does an amazing job at drawing circuits. I just love it. So here you go. Here's what the circuit, the optimized circuit that was obtained in the previous round with the VQE for this fragment looked like when we show it with Qiskit. And finally, it's very simple to send something to a quantum device. We have what we call QPU connections in Tangelo that are essentially simple interfaces that connect you with all of these services. We don't do any magic, as much as I would like it to look like magic. In reality, we use the open source toolkits and interface provided by Amazon, by IBM, by IonQ, you name it, and we just make it as easily as possible for you to use. For example, here, I think the runtime probably has disconnected. What if I try to run this again? Am I going to get an error? No, I'm not. Here's what I'm doing here. I'm going to essentially throw a quantum circuit at a device or a simulator, because I don't want to wait. A device would put me in a queue, available on IBM Quantum. So I'm importing a class called IBM Connection. I'm using a personal token. You cannot see it fully because I have an account on IBM Quantum. Everyone can create an account, by the way, on this platform. Then I'm going to instantiate my IBM Connection, and I'm simply going to call the job submit function. I'm going to tell essentially what kind of job I want. Here, I want to simply look at my circuit from earlier, the one that I showed you, and I want to run it on a simulator with 1,000 shots, and I just want to essentially sample that circuit, right? And here I can provide some additional options, all in the style of what IBM done. I can query the job status. It's printed below. It was telling me that the job was running. And finally, I can get my result. And as you can see, we have an histogram. This is my personal account on the IBM Quantum platform. If I refresh this page, you will see that, there you go. I just ran a job 1 minute ago. So what you see here is me interacting live with that platform. Of course, if you pick a natural device, you're going to be put in a queue. It may take several hours for your job to complete and everything, which is why here I just use a simulator, but it doesn't take much more effort to do that. With that, I hope I gave you an idea of how all of these toolboxes come together for you to do interesting research around quantum chemistry with quantum computers. I have a bit more time, and I want to give you just a quick example of how. Let me skip to this slide quickly. There is no better validation than having people from your community and your colleague telling you about success stories. And if you remember, one of the big things about Tangelo is that it was designed to be an engine to accelerate research. And there was a few key steps in research that we wanted to be very efficient. There was this article found by my colleague Alexandre about graph QC, which kind of implements like a graph decomposition techniques on molecule, essentially to decide how to decompose it, and then use the problem decomposition technique and the variational quantum eigensolver to compute quantities of interest, like the ground state energy, again, because the community has been very interested in that problem. And Alexandre wondered, okay, can I do that with Tangelo? Is this easy? What do I need to do? And it was pretty easy. He realized that, you know what, actually all of the tools I need are already in the toolboxes, right? So I should be able to easily draw my tools from these toolboxes, assemble my pipeline, and do what these guys did in the paper. And wow, that was very quick. The entire code, for example, is about 50 lines. The left part here, don't squint too hard, is really specifying your molecule, and Alexandre discovering how to play with graph with a package in Python for the first time. And all the chemistry is on the right part. That's it. He just grabbed the problem decomposition technique, paired with VQE, and he was able to reproduce results from this publication very quickly. He was actually able to go further because it was leveraging our VQE that is very complete, provides access to a lot of options and everything there. So here's a great example about how when you see a publication that's relevant to you, you can catch up fairly quickly and maybe even go further. Speaking of which, there's a series of work, still VQE related, very active field, that was done by a group. And I thought it's a very example of how we can really keep up with innovation here. For example, from VQE, this group of people developed an algorithm called DAB-VQE. Everything in orange that you can see on screen is actually a publication, an original work, right? And we find that a lot of the time, within 24 or 48 hours across, like, a paper, we just read it and we can just implement or sometimes integrate it in Tangelo. From VQE to a DAB-VQE, it took just one file. And everything was built on top of VQE Solver, which means that it comes with absolutely all its options. Suddenly, boom, we have a very rich DAB-VQE. Then with an extra further line, boom, next publication, now we have Qubit Adapt, and we even support it with additional feature that we found was relevant to us. And then with only 14 lines in that specific case, suddenly, boom, what comes out from another publication, Tetris Adapt-VQE, is also now part of Tangelo and available. So that's kind of the potential speed at which you can keep up with the state of the art that is advancing very quickly and moving it forward that we're talking about in practice for researchers. I'm not going to go too much in depth, but same with fault tolerant. We have many building blocks here, and to build essentially an application that can seem complex at first, well, you have all of the tools there, and that can really speed things up. And the last example that I find fun is that, okay, I have an entire algorithm library, but is it easy to just run my algorithm on a device? Like, you can see that through many different providers right now, they kind of just offer you only a few algorithms through their interface to run on the device they offer. But hey, I want to do good research with chemistry and quantum computing. I need to kind of, separate them to an extent. And the idea here is that you can define your very own compute backend. Here, for example, I play the game with IBM, where I say, I'm going to use my IBM connection object I showed you earlier, and I'm just going to define two methods: how to simulate a circuit, how to compute an expectation value. And now I can literally just plug it into one of the algorithms from the library. And most feature of the algorithm or the entire algorithm can run now on a quantum device. Whether or not you actually want to do that in the current state of quantum computing is another story. But this custom backend could be anything you wanted. It could be any code that does any kind of pre-processing, post-processing, and use whatever you want to do the actual computation. And that's the power here, is that really you combine all of these interesting algorithms and features for chemistry, but also great freedom, I think, in terms of quantum computing and the platforms you want to use and what you want to model. I'm going to go back and wrap up this presentation because I've been talking for long enough. One thing that I really want to highlight is that there's tremendous power in open source community. We've seen adoption by users in both chemistries, but also more from the side of quantum for Tangelo that find it interesting as a tool, as part of the ecosystem. Again, Tangelo is one tool among many. And if you want really to leverage breakthrough in quantum computing, we encourage you to use it in conjunction with all the tools that you think you need. There's some people from chemistry company that have been collaborating with us for years, researching these kind of problems. People that provide access to hardware that are interested in connecting us to their platform to help people do more chemistry on them. And there are people developing solutions around quantum computing, around different aspects of it, that are interested to see what Tangelo can do to help them solve tough problems. So the real question now is, what will you do with Tangelo? You can use it for educational purposes, you can use it for hackathon, but you can also keep up with the state of the art and push it forward with your research. Tangelo comes with a community, and well, it's a very interdisciplinary community. You're going to need a lot of help in order to take it to the finish line and do cool stuff. Software development, quantum physics, chemistry, quantum computing, or just, computer science. So whether you're a newcomer or an expert, you will find something interesting. You will manage to benefit from that. Finally, well, don't hesitate to reach out to Sandbox to explore avenues together if that is something you're interested in, whether they're quantum or not. Because the bottom line is quantum and quantum computers don't exist by themselves in a vacuum, right? You need to leverage the entire array of computational techniques and what we know from chemistry, from the problem, in order to explore what it can do for you. And that's it for my presentation. Thank you very much. I hope you have some questions for me.
Thank you so much, Valentin. I think you did a good job. I think these talks are always a bit of a slog to get through, but I think the chat was engaged. I was engaged the whole time, and there were actually quite a bit of questions. So let's do our best to get through them all here. So there's quite a bit of interest. Megamake on our Twitch channel had a lot of questions. Let's get to the first one. So they're wondering, can we put enough water molecules, for example, into a current generation quantum computer with Tangelo to see the actual properties matching macroscopic physics, or is that still out of range? I think I know the answer to that, but what do you think?
That's a really cool question. Let's go to this slide. You can see a little picture here in the biochemistry and QMMM. When you're trying to model such complex phenomenon, well, the idea is that maybe the answer is not so much coming from the quantum computing side, but the kind of approximation of the kind of chemistry you're going to use. And for example, there are methods essentially that kind of approximate or put together all the interactions between a molecule and its environment. So maybe the right question is, should I put a bunch of molecules all together in a quantum computer in the first place? Can I approximate what my environment is doing through classical or from a quantum perspective, and then compute separately what it does with my molecules in the right algorithm? For this particular question, the example we have, for example, using a technique called QMMM that really approximates the interactions between the environment and the molecule. Maybe that's more promising than trying to squeeze a bunch of H2O molecules, which I think right now is out of reach for quantum computers. Hopefully that answers the question.
Yeah, I think so. Sorry, your username again, MegaMake, right? MegaMake, if that doesn't answer your question, I think Valentin will be on the Discord after, so feel free to poke a question there. There are some more questions here from Ket Punto. Hey, one problem I have had when trying to run VQE on real hardware is that it is very difficult to predict how much it will cost me because I don't know how long it will take to converge. So can you estimate with Tangelo the number of runs that will be necessary, or is there any resource estimation built into Tangelo?
I think that's a very tough question. Even if we had the perfect simulators, I don't know myself how I would go about that. I think this is why it's very hard right now, because hardware, of course, are noisy, so you don't know where your convergence is going to take you. That is why I think we need to go beyond, for example, VQE, or try to think about utilizing quantum hardware a little bit better and researching this thing. Unfortunately, I don't have a problem. I think other packages, other people have researched that from a theoretical perspective a little bit better. I know that for now, in terms of VQE, we do not have such advanced functionality.
All right, cool. Another question from Dentucky Kirby on our Twitch. So Tangelo is open source. Is there capacity on your guys' end to deal with PRs from external contributors? Are there any issues, bugs, or features that are good to get started with if I wanted to contribute?
Absolutely. We'd love that, actually. This is, again, a fully open source project. Absolutely anyone can come talk to us, suggest a feature. It's actually great because we developed this as an engine to accelerate R&D, our R&D, but by extension, other people's R&D. But we don't know what interests you, right? We have a sense of that from what we see from the community. But if you want to study some particular problems, feel free to reach out. And even better, feel free to try to contribute this feature. We'll be there to guide you because we know Tangelo very well, and you probably know very well what you want to study. So yes, please go ahead. We'd love that.
Nice. Okay. Maybe one more question here from Andresu Lead. I think this is asked towards the end of your presentation. What is the chemical rationale, if there is one, behind fragmenting a quantum circuit derived from chemical calculations into smaller circuits? Does this fragmentation significantly impact the accuracy of the results?
Great. Again, I think this is really a chemical modeling question. All of these methods you see here have different approaches. For example, open shell DMET is like this iterative process that is good usually for strongly correlated system. Onium is going to be something that physically kind of breaks your molecule into different subsystems, cap the bonds, and then can treat them at different levels of accuracy. While QMMM is something that approximates the entire environment with, for example, a force field, and combine that with a high accuracy quantum algorithm on your molecule. Really, it depends on your system. It depends on the scale and the kind of chemistry you are looking at. I think that's what makes it challenging, and what makes the tools useful is that we're trying to equip you to kind of explore that and form an idea. But there's no guarantee. I'm not a chemist myself. People have a better answer than that, probably more insights. But as far as I know, it's the adventure. We're exploring.
Cool. All right. Well, I think that'll do it. That's all we have time for right now. Again, Valentin will be on the Discord. So if a question you asked didn't get answered here, go to the Discord. We'll put the link in the Twitch chat for you guys to head over there. But for now, Valentin, we'll say goodbye. And j'espère que vous avez une bonne après-midi et une bonne soirée.
Merci. Merci, Essek.
All right. Cheers. Bye.